Hello and welcome to my lesson. I'm Mr. Johnson. This is one of my 20-minute lessons, and this is on radioactive decay, which forms part of the radioactivity unit for GCSE physics. Just going to share my screen with you now, and we'll get started. Here we are. Okay, so what we should be hoping to do by the end of this is understand what happens during radioactive decay. So by that I mean you should be able to explain and describe what happens in alpha, beta, and gamma decay, explain what happens to atomic and mass numbers during the radioactive decay, and finally be able to construct some nuclear equations using principles to help you do that. So when an unstable nucleus changes and emits particles, the atomic number can change. If this happens, then the atom becomes a different particle or a different element. For example, when an alpha particle is emitted, the mass number of the nucleus goes down by 4 and the atomic number goes down by 2. Now, this is important because once that happens, then the element moves along according to the periodic table. Its mass goes down by 4, the atomic number goes down by 2, so it moves back along the periodic table, depending on what element you started with. This is radium. Radium would return into a radon nucleus because of the emission of the 2 protons and the 2 neutrons, and it would have a mass of 4 less than the radium nucleus with a charge of 2 plus less than the radon nucleus. During beta minus or beta negative decay, a neutron changes into a proton and an electron. The whole point of radioactive decay is to make the nucleus stable. With alpha, you've got too much mass and too much charge, so it loses mass and charge in one particle. With beta minus, then there's too many neutrons, and the neutrons break down. They change into a proton and an electron. Now, what you've got to remember is, because what confuses people sometimes is the issue that a neutron has no charge. A neutron has 0 charge, so somewhere in the neutron there is a balance of charges. And if a neutron changes into a proton, which has a positive charge, to conserve that 0 charge, it has to get rid of the negative charge. This is where the electron comes from. This happens in the nucleus. It's not in the shells. So that electron is ejected from the atom's nucleus and out at high speed. This then removes energy from the nucleus. The atomic number increases by 1 because we've gained a proton, but there's no change to the mass number overall now because the proton has come from a neutron and both of them had the same mass at the start. In beta positron decay or beta plus decay, it's the same idea, but instead of it being too many neutrons, so a neutron changes into a proton, there's too much charge, there's too many protons, so the proton becomes a neutron and it emits the positive charge that it's getting rid of in the form of a positron, which is the antimatter equivalent of an electron. Same properties as an electron, but the opposite charge, charge of +1. Now, because we've got rid or kicked out a positive charge, that means the atomic number of the element goes down by 1. But again, because it's a proton becoming a neutron and they both have the same mass, the atomic number does not change. So far, we've covered alpha, where we said that we've lost a mass of 4 and proton number of 2. And we've talked about beta, where the mass number does not change, whether it's beta minus or beta positron. But the atomic number does. In beta minus, the atomic number increases by 1, so the element moves 1 place to the right on the periodic table. And if it's beta positron, the atomic number decreases by 1, so the element moves 1 place to the left on the periodic table. So in beta minus decay then, what we've got here is a neutron in the nucleus of an atom, turns into a proton and an electron. The electron leaves the atom. The atomic number of the nucleus increases by 1 because now there is one more proton, sorry, I should say more, than there was before. In beta plus decay, a proton in the nucleus of an atom turns into a neutron and a positron. The positron leaves the atom. The atomic number of the nucleus decreases by 1 because we've lost a positive charge, and now there is one fewer proton than there was before. That's describing how alpha and beta decay occurs. And let's take a look at our next one, explaining what's happening to the mass and atomic number. So some questions. What happens to the atomic number and the mass number of radium when it undergoes alpha decay? If a nucleus underwent beta decay, what would happen to the mass number? If a nucleus released a neutron, what would happen to the mass number? During beta plus decay, what happens to the atomic number? And during beta minus decay, what happens to the atomic number? This lesson is linked inherently to your understanding of the properties of the subatomic particles. You have to understand what each one has in terms of mass and charge for you to get this particular unit correct. So what happens to the atomic number and mass number of the radium when it undergoes alpha decay? Even if you don't have a periodic table to hand, you can still say, well, an alpha particle has 2 protons and 2 neutrons. That's what it consists of. So the mass number is going to decrease by 4, and the atomic number will decrease by 2. If a nucleus underwent beta decay, what would happen to the mass number? Now, the convention states that if they're going to talk about beta positron, they will call it beta positron. So beta decay, in this case, would normally mean beta minus. But it doesn't matter in a sense either way, because it's asking what would happen to the mass number. Beta decay, whether it's positron or electron, involves the conversion of, for electron, a neutron to a proton, and for a positron, a proton to a neutron. Both of those have the same mass. So beta decay would not affect the mass number. It only affects the atomic number. So there would be no change for question 2. Question 3. If a nucleus released a neutron, what would happen to the mass number? Well, neutrons have a mass of 1. So if a nucleus releases a neutron, the mass number would go down. Note that it's not asked anything about the atomic number here, but in the event that the atomic number was asked about, neutrons have no charge. The atomic number relates only to the protons, so the atomic number would remain unchanged. For extension questions, during beta plus decay, what happens to the atomic number? Well, beta plus decay, it affects the atomic number because a proton has been turned into a neutron, and so the atomic number goes down by 1 because we've lost a positron, which carries away a positive charge. Whereas for beta minus decay, the opposite occurs. A neutron turns to a proton, so we've gained a positive charge, so the atomic number increases by 1. If a neutron is ejected from a nucleus, the mass number goes down by 1, but the atomic number does not change. Nuclei can also lose energy as gamma radiation. We've talked about this earlier in earlier lessons, but gamma radiation occurs when the nucleus has too much energy, but the particles are not undergoing alpha or beta decay. It's more like a nuclear quake, if you like, a kind of earthquake, because it's rearranging itself. And as it rearranges itself into a more stable energy configuration, the extra energy that it's got that it needs to get rid of is emitted in the form of a gamma ray. This then helps them make the nucleus more stable, but it does have no effect on either the atomic number or the mass number of the nucleus. So taking a look at this, alpha particle, again, it's really important to understand the properties of this to be able to do it. So alpha particle has a mass of 4 and a charge of +2. Beta electron, mass of 0, relative charge of -1. Positron, mass of 0, relative charge of +1. Now here we're talking about relative mass of 0, 0, but you might recall from earlier or from in your studies that we have mentioned that it has a mass of 1 over 1,835. It's considered to be negligible, so we can treat it as 0 in this respect. Neutron, relative mass of 1, relative charge of 0. Knowing then those particle properties, it helps us to work out what changes they cause in a nucleus, where alpha, Because it has a mass of 4 and a charge of +2, the mass number decreases by 4 and the atomic number decreases by 2. Beta electron, because it has a mass of 0 and relative charge of -1, then the mass number does not change, but the atomic number increases by 1 because we've got rid of one electric or one electron, one negative charge. So we have one more proton than electron. Positron is the opposite of beta electron. Mass number does not change, atomic number decreases by 1. And finally, the neutron, well, there's 0 charge and a mass of 1. Mass number decreases by 1, but the atomic number does not change. And that's our second point. Covered, explain what happens to atomic and mass numbers during decay. Our final one now, construct nuclear equations. A nuclear equation shows what happens during radioactive decay in a similar way to a chemical equation or a symbol equation in chemistry describing what's happening during a chemical reaction. In physics, a nuclear equation shows what's happening to the nuclei of atoms during a radioactive decay process. Just like in chemistry, the equation has to be balanced. The total mass number must be the same on each side, but we also have to make sure that the total charges are balanced on each side as well. It's the same idea of conservation of mass and conservation of charge. Just to make sure that we are on the same level, I have included here a symbol and particle table, just like we had before. Just move that out of the way. And we've got the symbols and the particles for various subatomic particles. The atomic or proton number for a nucleus or an alpha particle also presents the amount of positive charge. We give beta particles and positrons a -1 or a +1 to indicate the charge. So as you can see here, alpha, symbol A or 42He, because as we've encountered earlier, it's a helium nuclei. Beta minus, we use the symbol E for electron, and it has a mass of 0, so it's 0 on the top, and a charge of -1, so -1 on the bottom. Positron, again, beta plus. We use the symbol E because it's the antimatter version of an electron with a mass number of 0 and a charge of +1 on the bottom. Neutron, its symbol is literally N, and we can use a mass number of 1 and a charge of 0 on the bottom, which isn't clear there, but we can do it that way too. So as an example, radium-226 emits an alpha particle. What is the other product? Now, radium-226, 88, the symbol's given to us there with mass and atomic numbers. And we've got the atomic and mass number of the helium nuclei. So we've got to remember that they have to balance the masses and charges on each side of that arrow. This means that if the helium has a mass of 4, then the product must have a mass of 226, take away the 4, which would be 222. In terms of its atomic number, radium has 88 as its atomic number. We have 2 with the helium, so 88 minus 2 means that our unknown product must have an atomic number of 86. And if we take that through, then our radon-226 88, when it decays via helium, radium would make radon, which is 222 86. And we can see that at the base there. The 226 plus the 4 from the helium makes, or minus the 4 from the helium makes the 222 for the radon, and the 88 minus the 2 from the helium makes the 86 for the radon. Incidentally, you're not expected to work out and know exactly where it should go. You will be given the atomic symbols of things to use when calculating in the exam nuclear equations. So, as an example, we have a couple of different nuclear equations here. First one, beryllium. Beryllium-13, 13-9Be, emits a neutron, 10N. Now, because it emits a neutron, 10N, then its mass number will decrease by 1, meaning we're going from beryllium-13 to something 12. But its atomic number does not decrease because the 9 protons present in beryllium are not affected by the ejection of one neutron. It has no atomic number. So in this case, we can write it like this. 13.9 Be, arrow 10N plus 12.9 Be. Second example, fermium-258 decays to californium-254. Well, again, looking at this now, we've gone from 258 to 254, 100 to 98. The question doesn't tell us how it's decayed, but it does give us an indication that we're starting with an atom of 258, 100 fermium and changing to 254, 98 californium. And those of you that have followed the rules know that the conservation of mass and charge applies to this. So from 258 to 254, I've lost a mass of 4. From 100 to 98, I've lost a mass of 2. Automatically, that tells me 42 He. This is decayed via alpha, and so my equation would look like this. 258, 100 fermium, arrow 42 He plus 254, 98 californium. Finally, our third one, thorium-234 decays to protactinium-234. Again, it's not told us how. We're expected to work that one out. But if we look at the symbols that we've got, TH90 is decaying into something plus PA91. Well, straight away, looking at this, I'm thinking, right, the atomic number has increased by 1. That then suggests a beta decay process. And if we think about this very carefully, it's beta electron, the decay process, because that is the neutron turning into a proton, so we're gaining a proton. But the mass of the thorium and protactinium stay the same because in beta decay it affects the atomic number, but the mass is unchanged. And that's the end of it now, constructing nuclear equations. I hope this has been helpful, and thank you for your time. I hope to see you again. Take care now.